The collaborative BIM project is an office complex development on the site, which is parking lot next to Taylor's commercial block in Taylor's University Lakeside campus. Our task as a design team is to develop our preliminary design in compliance with LOD 200 requirements and to use relevant BIM operating tools such as Autodesk Revit and Autodesk Navisworks. The building was designed and constructed using BIM process to allow collaboration among architects, interior architects, and quantity surveyor. The project includes two 5-story office tower blocks designated by two teams, with on-ground and elevator connection. Our group collaborated with Group K, where they design Block A and we're in charge of designing Block B. Our 5-story office building implemented an end-core layout and is supported by reinforced concrete framing, which allow the building to have an open floor plan that provides flexible office workspace. Material used in the building includes brick, cement, glass, wire mesh, and plaster. Not so long ago, building a world with harmony came with a few twists, accuracy interpretation, misunderstanding, but time have changed. The Building Information Modeling (BIM) helps each stakeholder, client, architect, expert, and end user of a project to share the same vision from design to the usage of a building. But how different are traditional and BIM methods? In traditional methods, data and ideas are pretty unorganized, which result to time wastage. And the lack of collaboration to communicate, the chances of errors are at high risk. Followed by the inaccuracy of data can cause a delay in project and more money spent. Without the exposure to new technology advancement, it is hard to detect clash collision in a project, resulting to a long duration of administration approval, and lastly adding cost and time in a project. However, using BIM method, it is efficient as data are stored in a cloud server, which then distribute to multidisciplinary collaboration with accurate data share. The use of technology it is more engaging and flexible as messages are simple to analyze. The accuracy in data result to project able to meet today, all thanks to the software in improving the delivery of data. It helps to detect any clash detection at the early stage before the start of construction. We first by evaluating the design option. With 3D modeling, it allows users to analyze structure and improve workflow where changes can be made easily. With collaboration, it allows interactive testing while choosing the most efficient material choice and allows users to focus on delivering the best project possible. With delivery of the best outcome, it allows clients to engage better and understand better through exploration of vision of the building. It also helps architects to save time and cost with the use of cloud server to deliver the most efficient outcome. With BIM, it pushes the boundary by collaboration with structural engineers and simulate testing. It enables architects to explore two different construction techniques, deliver and conduct document in assurance of success and accuracy, with a complementary of 3D laser scanning of models that can benefit users to visualize and engage better in the success of the project. Lastly, it also minimizes the burden in the project where architects share the same CAD file to enable efficient workflow. Case study of the BIM implementation process in Malaysia, IBS Engineering Company, is carried out as a direct reference for the BIM environment. The first stage of the process starts by conducting an early review of the BIM software. SECAD, Revit Structure, and Tekla Structure are the three items of software chosen for employee training. Next go with the BIM team training. Concurrently with the early review of the BIM software, the company have identified 4 personnel to be trained as BIM designer who focus only on BIM modeling skill and 3 personnel to be acquire the modeling skill but to also acquire deeper skill to become Revit administrator. The skill include the component library development, troubleshooting skills, software configuration and administration, also the management side of BIM. Criteria evaluation is done after the training. The evaluation criteria were developed based on the user requirement, and a few of them are mentioned as following, which are the user-friendliness of the software, the flexibility, the interface of the software, the ease of use of the software which is related to the time that is required for achieving appropriate modeling skill, customization of template and components, and the interoperability of the software. Followed up by the BIM software selection based on the evaluation route, Revit Structure is chosen as the BIM software for the company. Although Revit Structure features less IBS-related function, however, the similar interface with CAD, which come from the same company, represent the biggest advantage where most of the personnel feel very comfortable to be working in a Revit Structure. Additionally, The ease of use to customize the IBS component and reasonable cost of investment features as the biggest advantage, justifying the decision of the company to go with the Revit structure. At the time of study, the company had acquired three Revit structure licenses. With the decision made, 3 out of 7 trained personnel of the company were assigned to attend the complementary training that was provided by the software vendors for further skill development. This timeline showed the weekly milestone for 8 weeks when conducting and experimenting BIM with multidisciplinary coordinators. These are the weekly completion for each week. From the line shows the start to the end of each task. Our team distribute ourselves to each responsibility roles, where BIM manager aims to provide mentorship and practice and oversees the BIM implementation to MLE members. She then support and organize the project distribution to improve the best practice and workflow throughout the 8 weeks of the project. BIM modelers are responsible to document and follow BIM standard and document weekly progress, along with detecting any clash detection. Also produce relevant models to MLE members based on programs and design analysis from BIM members. Lastly, are the BIM coordinator. They are responsible to manage and coordinate information and ensure the workflow and execute plan of BIM to MLE members. Collaboration and communication are keys to provide a successful proposal documentation for MLE members to inform and understand the proposal of updated weekly tasks and progress if any changes are made. Lastly, to provide any support and assistance on BIM modeling and clash detection from BIM modelers in order to achieve a successful project outcome. In our schematic design, we have produced drawing with the consideration of views, accessibility, sun, and wind path. As brief require, we decided to use N-core wall system as our service core in the office building. The reason we desired an N-core wall system due to three main concerns, as to maximize the spaces, to maximize ventilation, and natural daylighting in fire lobby as well as utilize the floor area connecting to the next building. In office building, we are using exposed building to reduce finishes cost while preserving the aesthetic of the building, reduce carbon footprint, as well as require low maintenance. The build-up process of the 5-story office block start up with the minimum 12 depth cast in situ board pile foundation as the superstructure of the building. Structural ground slab with the concrete cord C25 or C30 as the base of the ground 230 mm, reinforced concrete load-bearing wall built up. The service core of the office also acting as the core structure for support. Reinforced concrete columns and beams form the structural frame of the building. Concrete floor slab with C25 or C30 concrete coat are loaded on every levels. Facing brick are used for the material of the external wall with the purpose to remain the exposed texture of the brick as the building facade. Concrete hood with plastering finishes clad on the wall for aesthetic purpose. Next follow with the installation of windows and doors. External cast in situ fire staircase is located at the north end of the building as the primary escape route. Stainless steel mesh staircase cladding is installed for safety purpose and the runway ventilation. Complete with the component at roof level for service use. Steel beam structures connecting bridge connect both office block at third level. With the addition of the vegetation and the vehicular path, it completes the environment and the circulation for the user of the office block. The building consists of 4 main components, which is substructure, shell, interior, and service. For substructure part, the foundation is made by C35 concrete piling foundation and precast concrete two-way slab with finishing for the slab. For shell, it started from fire staircase running through 6 levels and have 5 landing with 900 mm height stainless steel balustrade and railing. Fire staircase is covered by plain square woven stainless steel wire mesh with 15 mm opening. For roofing, it is made up of concrete flat roof up to 3 degrees with hidden gutter system. Exterior window is consists of double casement window with fixed glass and fixed glass window located at office area and 2-panel toilet top hung awning window located at toilet, while exterior door located at main entrance and side entry, also fire staircase. Also, 150 mm structure bond half facing brick wall for exterior wall. Next, 900 mm thick facing brick parapet wall is constructed above plan of roof. For interior part, it is made up of 150 mm brick wall with 12 mm thick plastering on both sides to engineer's detail. and also 80 thick gypsum board toilet partition. Furthermore, interior door consists of single-leaf wood swinging door at the service core. For the service part, it consists of both fire lift and service lift with 6 passengers located at the service core.
The ground floor plan shows the vehicle entries to the building from south, while the north serves as a service lane. The office buildings are connected along a central open plaza. The core of the building is placed at the north end to allow more spacious and flexible office workspace. The elevated connecting bridge is located at the third floor to allow a better accessibility between two building blocks at upper floors. The overall building height is about 21 meters, with lift motor room located at the top of the roof floor. The ground floor has a double volume height of 8 meters, while the rest of the building above is 4 meters height. Both office blocks use the same design language for the exterior facade. The interior view of the ground floor are of double volume height of 8 meters. This image shows the view of a steel structure connecting bridge to our building. To execute our project, Revit Cloud Work Sharing are used to improve the workflow and ensure our building model is in the latest version. This helps to improve communications and efficiency with the entire team. With cloud sharing, the Synchronize tool helps to save any changes made in the model to ensure the team's building model is up to date. Using the Relinquish All Mine tool, it allows other members to have the permission to edit the central model when accessing the cloud sharing. In Navisworks and Clash Report, clash detection is a technique used to inspect any interfaces in the project model to reduce the risk of human errors before the start of construction. In our office model, BIM modelists analyze clash reports using Autodesk Navisworks after the model is finalized and completed. Aside from clash detection, the use of Autodesk Navisworks helps to improve the communication with clients and consultants using 3D presentation techniques and models to engage better. In the clash detection, hard clashes are detected in floor to column, ceiling to column, floor to show walls, and beam to show walls. These clashes are detected due to the imperfections of the digital model. However, it can be ignorable where it does not affect the construction process. Some odd clashes detected are door clashing with walls and mullion clashing with glass, which occur due to the mistake of a Navisworks. In conclusion, implementing BIM in the practice workspace helped to save 50% of time in the design stage, 33% in the construction stage, and 20% in the operation stage. At the early stage, the selection of appropriate BIM software is important to perform the task, followed by the involvement and participations with trust, respect, and commitment to achieve a success under the BIM environment. To implement a successful BIM, collaboration, personal commitments, motivations, and practitioner behaviors are to considered to increase the diffusion of BIM. In current Malaysia construction industry, we face challenges in terms of project delays, cost overruns, and low quality, which urge to be solved. Despite the acknowledgement of BIM, practitioners are reluctant to adapt the practice. However, the construction players believe that BIM should be enforced to produce a desirable outcome during a project. Government policy is viewed to in line with the construction stakeholders' perceptions of the value gained by the BIM implementations. But with the current Malaysian construction industry, CAD-based workflow are heavily relied on, where BIM implementations somehow increase the difficulty in shifting the company's workflow from the conventional construction practices into the BIM-based technology. We have come to the end of our presentation, and thank you for listening.